Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. This is a continuation of the previous two sessions on process management. Remember, in the previous part we talked about how to create a child process in Unix-based systems using the fork system call. And we also talked about as how the parent can wait for the termination of its child processes using the wait PID, and other wait family of system calls. The agenda of today's session is overwriting process address space using the exec family of calls, effect of fork and exec on process attributes, writing our own system library function, job control, process group, sessions, and terminals. Let us start with the exec family of functions. Well, dear students, a process may overwrite itself with another executable image. When a process calls one of the 6 exec functions, it is completely replaced by the new program, and the new program starts executing from its main function. There are 5 library functions of exec family and all are layered on the top of exec VE system call. Each of these functions provides a different interface to the same functionality. Remember, there is no return after a successful exec call. The exec function returns only if an error has occurred. The return value is -1 and error number is set to indicate the error. Well, these 3 functions are called the exec L family. The L after this exec means that command line arguments to the new program will be passed as a comma separated list of strings with a null character at the end. The first argument to all these functions is the name of the executable, which on success will override the address space of the calling process with a new program from the secondary storage. After this first argument, we have the comma separated list of the arguments, and finally we have a null over here. The P, if used, stands for path. It means that the program specified as the first argument should be searched in all the directories listed in the path variable. However, it is always better to use absolute path, which is more secure. The if used over here requires another third argument, which is the environment. That is, after the comma separated list of command line arguments, we have an array of pointers to null terminated string specifying the new environment of the program to be executed. And for the remaining these 2 functions, the caller's environment will be used. And these 3 functions are called the exec V family because we have a V over here. This V actually means that after the exec, after the program name, the command line arguments are not passed as comma separated list. Rather, the command line arguments are passed as an array of pointers to null terminated strings. And the P, of course, means that this program name will be searched in the path environment variable, and this E means the third argument, that is the new environment. All these functions, if successful, never returns. And in case of error, returns -1 and set the error number to appropriate error. And the reasons of failures are mentioned in this table. You can see the man page for detail, of course. Let us move on to the Linux terminal to practically understand the concept involved. Let me show you the first program that I have written for this purpose. Well, this program shows the basic usage of execlp. The parent process over here do a fork, and the child process calls execlp function. And the first argument is the name of the program, and we just mentioned the program, not the absolute path name over here, because we have a p over here. This is the first argument to this program, which is the name of the program. This is the second argument, that is -l, and this is the third argument, that is /home. And finally we have a null over here. Once this execlp will be executed, the child process address space will be laid out with another program, and that is the ls program. And if this is a success, this line will never be printed. So once the child terminates executing the ls program, the parent process comes out of the wait and prints hello I am parent, and then finally returns 0 to the bash program. Let me compile and run this program. Sorry, gcc exec1.c, and let me run it, and you see it is executing the ls-l/home program. Let me run it like this, and you see there is no difference among the two other than this line, hello I am parent. Let us see another program to see the usage of execv now. exec2.c. Almost the same logic. The only difference is we are using execv. We are calling /bin/ls program. And over here you can see there is only one single argument, which is a vector to a comma separated list of the command line arguments to this program. So this is the main difference between the execl and the execv family of the calls. The parent of course waits and finally prints hello I am parent. Let us compile and execute this program as well. And you see the same output. Okay, so let us see one more program to see the usage of execle, exec3.c. Well, over here in the child program we are executing the calculator program, genome calculator, which is located in usr bin directory. And you can see the last argument over here is the external variable environ, pointing to the shell environment variables. You can always change the environment variables and then pass a pointer over here. And this is the execle call. And rest code is same. Let me compile and run this. exec3.c ./a.out. And you see the calculator program is there in front of us. Let me close this, and we have the parent executing, printing hello I am parent, and the shell is there. Let's see another program, exec4.c. Okay. You can see in the main function over here, we are creating the argument list. We are just creating the argument list, and then we are calling the execute function. This is our own defined function execute, and we pass this character pointer argument list containing all these command line arguments. And here is the code of the execute function. And over here I have used the switch statement. After doing the fork, I check out if the fork is returning -1, so I print the error message. If fork returns 0, that means this is a child process. The child process will execute this code, and the parent process will execute this code. The child process is using execvp and executing this first argument that is passed to this, that is /bin/ls, and the rest of the arguments are passed over here. The parent waits using wait PID this time, and the status is saved over here. And I'm right shifting the status variable by 8 bits so that to get the exit status, and this execute function is actually returning the exit status of the child process to the main function received in this RV, and the main function is finally returning the same value to the bash process. Fine, let me compile this program now. exec4.c, let us execute it. That is it. And if I do echo $question mark, you see this is the 0 value which is returned by the main function to the bash process. I hope the working of exec family of functions is quite clear. So let us fall back to the slides now. Now let us quickly talk about the process attributes after a fork and an exec call. Well, dear students, after a fork, the child does not inherit the PID and PPID. After the fork, the child has its own PID and the parent PID. However, other IDs like PGID, session ID, real, effective, and saved UIDs, they all are inherited from the parent to the child. You can see these are inherited after a fork. So as far as the exec is concerned, after a process do an exec, all these IDs are preserved. However, we can certainly change the effective and saved SUIDs. And I think we have talked about this in some previous session. Similarly, if we talk about the process address space after a fork, the text code section is shared after the fork among the child and the parent process. However, the stack, data heap, environment, and all the memory mappings, they all are inherited after a fork, inherited from the parent to the child process. And after the child process do an exec, nothing is inherited. Rather, the new process has new code, stack, data, and memory mappings. Point to be noted is that whether the child after the exec gets the environment of its parent or has new values of environment variables. And this is dependent, of course, on the type of the exec call that we have used. So I hope these two tables are making sense to you all. Let's see some more attributes. Well, this slide shows us as to what happens to process attributes related to files, directories, and scheduling and other resources. Let me describe this last line, which says that if the parent process has registered some exit handlers, they are inherited to the child after a fork, but not after an exec. Well, dear students, you can write programs as proof of all these concepts, but let me prove practically that exit handlers are inherited after a fork, but not after an exec. And for that, I have two examples prepared. Let us move on to the terminal, clear the screen, and see this first example, exit_fork.c. Okay, you can see the main function is registering a function called exit_handler using @exit. Then the main is calling fork. This is the code of the child process and this is the code of the parent process. And now if the exit handler is inherited by the child, so the child will also execute this exit handler on its termination, and the parent, of course, it will certainly execute the exit handler. Let's compile and see whether this maps to what we are saying. GCC exit_fork.c ./a.out. Well, you can note that the parent and the child both have executed the exit handler. The child has terminated first, so it has executed the exit handler, and then the parent process has terminated, so it has also executed the exit handler. Let us map the same concept and see what happens after an exec call. Let's vim the code exit_exec.c. This is the same piece of code. The exit handler is registered using @exit, but after the fork, the child process is doing the exec LP call. So now we will see that this exit handler will not be executed by the child process. However, it will be executed by the parent, which will prove that exit handlers are not inherited after the exec call. Let me compile and execute this program as well. ./a.out. Well, you can see this is the output of the ls program, which was exec by the child. No exit handler was called by the child process. However, the parent has executed the exit handler. Okay, so far so good. Let us fall back to the slides. Well, probably in some previous session we have talked about the system call, and we all know that it is used to execute a command specified as an argument over here. And remember, actually what happens is it executes the bin bash program with the -c argument. The main cost of the system is, of course, is its inefficiency, because executing a command using system requires creation of at least two processes, one for the shell and other for the command it executes. Let us move again on the terminal and see some sample programs that make the use of the system library function and see how powerful it is. Of course, inefficient. Let me clear screen. System1.c. Well, a very basic program. The main function is receiving one command line argument, which is passed to the system. It executes and it says done, bye bye. That's great. Let us compile this. System1.c ./a.out, and let me pass a string pwd, so it is executed. Let me run it again with the command who am I. It is executed. Let me execute it again with the command, let's suppose genome-calculator, and it also gets executed. That is great. Well, the way we can execute a program using system, we can always execute a script, a bash shell script, or a script in any language using the system function. Let's see that as well. System2.c. Well, in this over here, you can see we are trying to execute a script using the system, and the name of the script is script1.sh. Let me show you that script as well. And this script basically contains 4 commands. Let me compile this program, system2.c, and let me execute it. That is great. You see, the system library call has successfully executed the script from within our C program. Let us see one more program. System3.c. Well, this is a very marvelous piece of code that within just 4 or 5 lines it is emulating a complete shell. You can see within the main function what we are doing is we are doing this. Within an infinite loop, we are printing the prompt, which is PUCIT. We are getting a command from the user using fcat-s, and then we are passing that that string which we have received from the user via keyboard to the system function, and this process continues. So let us see this program in action. GCC system 3.c./a.out, and you see now a program is running. The prompt is there, and it is asking us to enter an input. Let me say PWD. So it is executed. Who am I? It is executed. Let me pass more than one argument. ls-l/home. It executes. And if I press Ctrl C, I quit. Let's see the program again. System 3.c. So a marvelous program that just emulates the working of a shell. An infinite loop, printing the prompt, getting the command, and passing that command to the system call. That is great. So let us fall back to the slides again. Well, dear students, now we know how to use system function. Let us see if we can write our own system function using fork and exec. Well, to do this, just note that the -c option to the bash program provides an easy way to execute a string containing an arbitrary shell command. And over here you can see the exec L, which is passed this program name, this -c option, and finally the command line arguments. I think I have prepared a piece of code. For that, let's move on to the terminal. System 4.c. Well, in this piece of code you can see okay, we have written our own function, mySystem, which is passed a string, and inside the main I'm just calling this function which I have written myself and passing a command string to it. Well, inside this function you can see I'm doing a fork. In case of child, I'm doing exec lp, and I'm passing it the command bin bash with a -c as option, and this portion over here, the command. So this portion actually will execute. So bin bash will take this string as command and will execute it. The parent will of course wait, and finally it will return. So over here I have actually written my own system function using the fork and exec lp. Let's compile this program and see it in action. ./a.out. So it works great. So I hope that you have now a very fair idea of how to system library function works. Let's fall back to the slides again. Well, before I talk about process groups, sessions, and controlling terminals, let me have a quick recap of job control states. Well, dear students, you all must be knowing that job control permits a shell user to simultaneously execute multiple jobs or commands, one running in the foreground and others in the background. A user on a terminal can use different commands to move these jobs between different states. Right now over here you can see this is a command which is running in the foreground. There can be many commands which can be running in the background, and we know that we can run a command in the background using the ampersand over here. There is another state that is suspended. We all know that we can stop a running program in the background, and we can always terminate a program. Let's see how we can move a job or process from one state to the other. First of all, we all know that we can pass a signal to the foreground running process by pressing Control plus C or Control plus backslash, which will send sig int and sig quit to the foreground running process respectively. So this will terminate the program. Similarly, if we press Ctrl plus Z character on the keyboard, it will send a sig TSTP signal to the foreground running process and will suspend it. That is, it will be stopped in the background. And if we send a BG command or the sig continue signal to a suspended job, it will start running in the background. And if we send a FG command or sig continue signal to a suspended job, it will start running in the foreground. So BG will continue a suspended job in the background and FG will continue a suspended job in the foreground. Similarly, if a job is running in the background, you can use the FG command to bring it in the foreground. And of course, we can use the kill command to send signals. And if we send a kill command using the signal sig stop, it will suspend a job which is running in the background. And finally, we can always kill a suspended job to terminate it. Well, now you have a fair idea about the job control states. Now let us move on to the concept of the process group, session, and the controlling terminals. Well, dear students, a process group is actually a set of one or more processes sharing the same process group ID. Every process group has a process group leader, which is the process that creates the group and whose PID becomes the PGID of that group. A child process inherits its parent's PGID, and the lifetime of a process group starts when the leader creates the group and ends when the last member of process leaves the group. A session. Well, a session is a collection of one or more process groups. A process session membership is determined by its session ID. Every session has a session leader, which is the process that creates a new session and whose PID becomes the session ID. At any point in time, one of the process groups in a session is the foreground process group, and the other process groups are called the background process groups. Terminal. Well, dear students, all processes in a session shares a single controlling terminal, which is established when a session leader first opens a terminal device. If a terminal disconnect occurs, the kernel sends the session leader sig hub signal. Well, this slide shows the relationship between the process groups, session, and a controlling terminal. Let's suppose that we are working on a shell and the PID of the shell is 400. This is the shell, the bash program, which is the session leader having PID 400. Its process group ID is also 400 and session ID is also 400. So this is one process group having only one process, that is the bash. And overall, you can see this is a bigger picture showing you a complete session. If I run a command find to find something from / I'm missing something over here. Let's suppose I make a find and I pipe the output of find to another program that is WC, and I run both these programs in the background. So what this command is actually doing is it is creating another process group you can see within this process group we have two processes, find and WC. And both find and WC, their parent is 400. PPID is equal to 400, PPID is equal to 400. That means the parent of both these programs is the bash process. So this is another process group. And the process group leader is, of course, find, the first process which is created over here. You can see the PID of find is 658 and the process group ID is also 658. The PID of WC is 659 and the process group ID is also 658 once again, the ID of the find program. So this is another process group having two processes. Let's suppose I run another command, and that is the sort and the unique command with a pipe in between. So this process, this program will run in the foreground. So this will create another process group. You can see over here, this is another process group having two processes, sort and unique. And remember, both these process groups have their session as 400. So we have a session having the session ID of 400, and this session we have three process groups. This is a process group having the process group leader as bash. This is a process group having the process group leader find, and this is another process group leader having the process group leader sort. Well, within this session we have three process groups, and this is the foreground process group, while these two are the background process groups. And this section 400 has a controlling terminal, and this is the information about this controlling terminal. I hope you have a fair idea about now processes, the process groups, and the session, and the controlling terminal. Well, dear students, from within a C program, you can use get PID and set PGID system calls to get the process group and change the process group respectively. These two calls, get PGID and set PGID, are used to retrieve and change the process group. Similarly, you can retrieve and change the session ID of a process using the get SID and the set SID system call. I'm leaving the proof of this concept as an assignment. You can see the man pages of these system calls for details. Okay. So that is the end of today's session. Hope it was informative for you all. If you have liked it, please subscribe to my YouTube channel and share it with your friends. Wish you all the best. Happy learning, and Allah Hafiz.